All right, let's see where we left off here. So like I said, we're going to finish off this chapter today. So last time we ended off talking about the thermal domain. We're basically going through the different domains. It's been a week and a half since our last lecture. So just to remind you, we're looking at the different energy domains. We're looking at the electronic domain, the fluid flow domain, the thermal domain. We talked a little bit about diffusion, and now we're going to finish up with the mechanics domain today. What I want you to be able to do in this module is to be able to analyze these different domains with equivalent circuit models. Let me show you an example of what we did. Okay, in the fluid model, you can model a microfluidic channel by using an electrical circuit where a current source represents the flow and these different resistors represent hydraulic resistances. Okay, so that's one way of modeling a fluid system using an electrical circuit. In the, moving ahead, I'm not going to go over all this stuff again. In the thermal domain, we talked about circuits to model the thermal domain. Okay, in this case, you have a current source, which represents a heat being generated in the system. If you recall with the microbolometer, you had a membrane, and when infrared light hits this membrane, it gets hot, so that's represented by this current source. And you have a thermal capacitance here and two thermal resistances here. Just as a reminder, what is this thermal capacitance? What does it represent physically? Stored energy, that's correct. So stored thermal energy is the fact that the object is hot. Okay, it's going to take some energy to increase the temperature of the object, and also the energy stored, the heat stored in the object can't go away instantaneously. So the temperature of the object can't change instantaneously, just like the voltage across a capacitor cannot change instantaneously. So it's modeled by this capacitance. These thermal resistances represent the heat flow paths where this pixel is connected to the substrate through these legs. Heat can flow through the legs. Okay, so from a purely thermal standpoint, this is heating up. Okay, and when that membrane is heated up, heat flows between the hot object to the cold object. The substrate is cold, so it flows from the membrane into the cold substrate here like this. That heat flow can be represented by currents in this electrical circuit model. Currents flowing through these two resistors basically model heat flow going from the membrane into the substrate. This thermal capacitance models the energy storage, the heat storage in this membrane. The advantages, remember, of thermal systems is that these thermal capacitances can be very small. So basically objects can be heated up and cooled very quickly at the microscale. All right, we finished off with the thermal domain here. Today we'll talk about the mechanical domain. Okay, and again, these concepts I'm showing you are, they're very basic concepts that you probably learn in undergraduate mechanics course, even in an advanced high school course. But it's useful for us to understand some of these basic concepts, especially those coming from different domains. So what we're going to get at here is that I also want you to be able to analyze a mechanical system using an equivalent circuit model and understand the scaling benefits of mechanical systems just as we've understood the scaling benefits of fluid systems, thermal systems, and so on. All right, so in the mechanical domain, we can just review a few essential concepts. Mechanical systems with rigid body mechanics, we're looking at the displacement and velocity and acceleration of some type of object. A very basic system can be modeled by a spring and dashpot. We'll get to that in a second, but we're looking at the movement of a mass. All right. Now, the different forces that a mass might experience, one is acceleration. So let's now look at some of the details of this. Let's say that you have let's say that you have a mass here, All right, we're going to draw what an accelerometer system looks like. By the way, does anyone know where accelerometers are, the most popular uses of accelerometers right now? What are accelerometers? What do they measure? Acceleration, yeah. And do you know where accelerometers are used a lot? The biggest, in the 90s, the biggest application for accelerometers were automotive airbags for detecting crashes. So when the accelerometer detected a large acceleration, that would trigger the airbag to deploy. All right, great technology for crash safety. But does anyone know what the big use of accelerometers are right now? Every one of you is using one.
Cell phone.
Cell phones, yeah, exactly. They're used in cell phones for when you pick it up, when you rotate your cell phone, your screens turn. Right? There are accelerometers built into certain phones for detecting like how much I'm walking. Like my Samsung Galaxy has, you know, the app that detects how many steps I've taken per day. Accelerometers are in things like Fitbits, you know, that also detect motion. They're everywhere. So the basic, I'm using accelerometers as an example because it's a nice example of a miniaturized system, which is very quite commonly used. The way that an accelerometer would be modeled, this is pretty ugly. Let me redraw this. You have a mass, okay, and that mass is attached to a cantilever. The cantilever has a spring constant given by K. All right. Now this whole thing is in some sort of housing, okay? And this cantilever beam is, one half of it is attached to the housing itself. I'm drawing a very simplified diagram of this. The mass is actually made of a material that's either conductive or it has an electrode on the bottom end like this. Most of the time the mass itself is just conductive. All right, so let's say we have a mass that has an electrode on it, and then on this side we also have an electrode. And this is connected to some type of circuit. And the circuit measures capacitance. What's going to happen to the capacitance here? Capacitance is equal to epsilon A divided by D. This is the distance D, the distance between the plates. Right? Now, let's say we take this whole mass here, so we're talking about this entire thing here, and we subject that to an acceleration. What's going to happen to this mass? Yes, Mohammed? It'll swing. That's correct. It'll swing up and down.
Yeah, so
That's correct.
these will be moved either smaller or bigger.
Absolutely.
And it will change the capacitance.
Exactly. Right. When this thing is exposed to acceleration, this mass is going to end up either moving closer to this electrode or farther away. That changes this distance d. Okay, and that distance d changes the capacitance, and you can have a circuit that measures the capacitance. So you can electrically read out the acceleration, because the force on this mass is equal to ma. All right, we'll go back to the equations here, but this is what the system looks like. Now, accelerometers are used, like I said, you have accelerometers in your cell phones, you have accelerometers in automotive airbags. They're everywhere. So in this is a good example because it demonstrates rigid body mechanics. Okay, you have a rigid mass in there that's attached to something that's holding on to it. That rigid mass is going to be subjected to acceleration, F equals ma, right, when you subject it to acceleration. This is a mechanical model, okay? So when, let's say this mass was attached to the housing here, and this whole device was accelerated in the upwards direction. Okay, so in the direction of x. The acceleration is happening in the positive x direction. So the first force we're going to talk about is that the force exerted on this mass is equal to mass times acceleration. Whatever acceleration was being applied to the entire system. That's the first force on this mass. The second force, well, let's do this one as the second force. The second force is that the mass is attached to a spring. Okay, in this case, you had the mass that was connected to some sort of beam element. Okay, these beam elements can be microfabricated. Right, this beam element is going to resist the mass from moving. It acts like a spring. Now, with springs, there's a very simple way that we can model springs is by using Hooke's law. Force is equal to kx. K is the spring constant of the cantilever, and x is the displacement. Okay, you imagine with the spring, the more you displace it, the more force the spring tries to pull back. So that's a simple law, Hooke's law. K is a spring constant, so the more rigid the spring is, the more rigid the spring is, the higher the spring constant is going to be. All right, so you have this force, you have the mass here, and then you have this resistor element, or this is a spring element, and that's represented by K. That represents a force exerted on this mass that's pulling back on it. It's being accelerated in this direction, but the force is pulling back in the negative x direction. The third force is the friction force. Okay. Now the friction force in this case, in the case of a simple cantilever beam, is suppose the mass is being accelerated in one direction. Now, let's say it's going in the upwards direction, since that's the example that we showed. Now there may be air molecules in here. Okay? So if those air molecules are there, the mass has to push aside the air molecules. Right? So the air molecules will actually damp the system. It's called a damping coefficient. All right, so that's where this force comes in. A frictional force or a damping force. That force is equal to BV. It turns out that it scales with the velocity. The faster the object is moving through the air, the more force is going to be exerted on it. It's like a drag force, right? If you imagine a car moving through a highway, faster it's going, the more drag forces there will be. So that's your frictional force, drag force. Force is equal to B times V. So if we look at all these three forces together, we have this this simple system here. The frictional force is represented by something called the dashpot. That's what this C is. Just to clarify, this C and this B are the same thing. So in this mechanical system, we have three forces at work. One force is acceleration dependent, force equals ma. Another force is velocity dependent, and then another force is displacement dependent. You can add all those three things up. So the force in the upper x direction, the acceleration force ma, is equal to negative bv minus kx. Okay, this is the force from the frictional force, and then this is the force from the spring. All right, and you can express that as a differential equation: m times d squared x dt. X is the displacement plus b dx dt minus kx equals 0. Dx dt is velocity, and then you have this this term here. So, reminding ourselves from our undergraduate mechanics class that this is just a basic differential equation. It's a second order equation, and it can be modeled by this system here. Very easy to solve these types of differential equations. This particular system will give you, if you recall, it'll give you a resonant frequency. So the mass can actually vibrate. The resonant frequency is the square root of k divided by m, and the damping coefficient is given by b divided by 2 times square root km. We'll talk a little bit more about this in a second. When you solve this system, basically you're either looking for the displacement of the mass divided by time, or you're looking for the velocity of the mass divided by time. Now, like in practical circumstances, what we'd be interested in with this accelerometer is how quickly can it respond, right? Like let's say you're using this accelerometer sensor for an airbag deployment. You need that thing to respond very quickly, right? So deploy the airbag in time. So these types of mechanical systems will have a frequency response, just like an electrical circuit will have a frequency response. So when we're analyzing these things, we're analyzing these equations here. One of the things we're interested in is how fast does the object move? How quickly does it get to its equilibrium position? Does it vibrate? Does it resonate? Okay, if a sudden acceleration causes the device to vibrate, at which frequency will it vibrate? It turns out a lot of accelerometer sensors take advantage of vibrations. They run the system at the resonant frequency because that's where you get the best energy characteristics or the least energy loss. All right, so this is the basic spring mass dashpot system. Of course, you can have much more complicated things. We're just going over the basics right now. Another important and basic concept is the beam bending of a cantilever beam, since this comes up all the time in MEMS type devices. So this cantilever beam is going to exert a force, right? And the dimensions of this beam and the rigidity of the beam is described by its spring constant K. Right, and the spring constant K is given by this equation here. K is equal to 3 EI over L cubed. And this E is the Young's modulus. So that's a property, a mechanical property of the material used to make the beam. It's the rigidity of the material. I is the moment of inertia. That depends on the geometry of the beam. It's equal to WH cubed divided by 12 in the case of a rectangular beam. For non-rectangular beams, like circular beams and other cross-sections, you can look this up in a book. There are, I think there's a book called Rourke's Formula for Stress and Strain that has all this information in there. It's all been solved analytically. They're exact equations. That's the moment of inertia. You notice that it's W times H cubed divided by 12. H is the thickness of the beam. So you can imagine what's going to happen if you have very thin beams, as is the case. When we microfabricate devices, we deposit thin layers of material, and then we pattern those layers. So devices, the thicknesses of the beams will be very, very thin. That equates to small spring constants. So things become flexible, things that you would consider to be rigid, like silicon is a traditionally rigid material. But if you make a very thin beam out of silicon, that silicon will bend. And then we have L cubed in the denominator. Okay, the longer the beam is, the shorter the beam is, the higher the spring constant. So another thing that happens at the microscale is if you're scaling down the length by the same dimension, then your spring constants will become larger. I'm sorry. If you're scaling down the thickness of the beam along with the length, then your spring constants will remain the same. If you only scale down the length while keeping the other parameters constant, of course your spring constant is going to jump way up. Right? It turns out that we'll talk more about the scaling of these devices. We'll get to that in a second. The damping factor here. So this system is described by this differential equation. If you recall from your differential equations class, the solution, you may have a system that's underdamped. You may have a system that's overdamped. This should read overdamped, by the way. Or you could have a system that's critically damped. Okay. Now, just to remind you all what the response of that is, if you were to take your system, so if you were to take this mass, for example, and just like tap it. If you were to tap the mass and then you were to plot the velocity v of t versus time, if you have an underdamped system, what will happen is that let's make this x of t. That's the displacement. In an underdamped system, from the moment you tap the beam, the beam will start to resonate at its resonant frequency. So it'll just basically vibrate. Okay. And in a perfectly underdamped system where there's no, this is if there's no damping at all, right? That damping coefficient B that we looked at previously, if that doesn't exist, this thing will vibrate indefinitely. It'll continue forever. So this is an example of an underdamped system. And an overdamped system, it might just look like this, where you displace it at time 0, but then initially it goes back to 0 displacement. And so this would be overdamped. And in the case of a critically damped system, you might have some oscillations that eventually die down. And until it rests. If you want to look more at physics concepts, this is another nice page from Hyperphysics. Any questions on this stuff? This is hopefully just a reminder of things that you've looked at earlier.
So the goal would be to have an underdamped system?
Good question. So the question is the goal to have an underdamped system? If you want the system to recover from whatever perturbation that you gave it, the fastest response, the system that returns to its initial state the quickest, would be the critically damped system. See, the overdamped system, it resists. The overdamped system would be if there's a lot of, let's say, if there were a lot of air molecules next to the mass. If it was a high pressure system, those air molecules would resist that thing from moving at all. The problem with overdamped systems is that there's a lot of energy loss. Right? It's actually resisting, those air molecules would resist the mass from moving at all. Okay. Now, a critically damped system is, well, an underdamped system is where there were no air molecules at all, in which case it would just oscillate indefinitely. There are certain situations where you would like the system to oscillate indefinitely. In the case of resonators, you actually want the system to be resonating without losses and with as least energy input as possible. The critically damped system is important when you want the system to recover from oscillations as quickly as possible. So initially there's some oscillations, but those oscillations die down relatively quickly. We'll see a few examples of the resonant system. So here's an example of a micromechanical system, the accelerometer that we just talked about. So you assume that an accelerometer is a proof mass that's attached to a cantilever beam. The beam bends when the proof mass experiences acceleration, just like I drew earlier. In this case, the arrows are sort of opposite here. The acceleration is going down, and the spring force and the damping force is going going up. Now this is a practical device. As I said, these accelerometers are in your mobile phones. You can see these types of devices here. You can also see these ST microelectronics accelerometers for airbag deployment, as I mentioned earlier. Some of the systems, these are examples of what the systems look like. I drew a very simple diagram in the notes here. All right, but sometimes these devices can actually be a little bit more complicated than that. The device that I drew here, this only detects acceleration along one axis. Right, the accelerometers that are in your cell phones and some of the sensors even in the automobiles are multi-axis sensors. So they'll sense acceleration in the x-axis, the y-axis, and the z-axis. We call those tri-axis accelerometers. This is an example of an accelerometer where you have some movable plates and then you have a movable microstructure here. This is what an example of what a system might look like. In the diagram that I showed you earlier, you had a single mass and just a single electrode. That's a good way to describe the system, but the systems that are used commercially, in order to increase the sensitivity, they try to increase the amount of capacitance in the system, right? So that you have more change. Let's look at what I mean here. You have a movable plate here. Let's look at this one, for example. When you have motion in the x direction, this movable plate has fingers on it, and located right next to the fingers are electrodes. Now, if you look at this this structure here, you notice that you have one capacitance here. All right, this is an electrode, and this is what's moving. You have an electrode up here, so there you have a capacitance formed there, and then you also form a capacitance here as well. So this is what's called a differential sensor. When the plate is moving up, what's going to happen to this capacitance? I'm sorry? Will it increase or decrease? It'll increase. That's great. It'll increase because capacitance is epsilon A over D. Right? So smaller distance means the capacitance will increase. At the same time, the second capacitance is going to decrease. Right? So you have one capacitance that gets larger, another capacitance that gets smaller. This is a differential way of sensing. It's a very accurate way of doing things. It's very good at rejecting noise. All right, so they have some differential sensing element here, and that the other legs of the capacitor works the same way. This is an example of, I believe this is a multi-axis accelerometer. Notice there are spring elements that would allow the proof mass to move in this direction, and even the z direction. Okay, these spring elements here, for example, will allow the device to resonate in this direction. These two spring elements here will allow the device, the proof mass, to move in this direction. And these elements here, this is kind of interesting, these elements will actually allow the device to pop up in the z direction, parallel to, or orthogonal to the surface. Okay. And the nice thing about some of these initial devices that were made is that the electronics were actually integrated right below the sensor. So the electrode was under there, all the detection electronics were there as well. Now, these types of devices, this sort of system is both a blessing and a curse, because when you put the electronics and the sensor on the same chip, there are certain advantages in the sense that you get your whole device done in one device, right? You don't need a separate chip for the moving element and a separate chip for the electronic element. However, this process is very expensive. So when they're trying to adapt a design and improve it, there's a lot of work that has to go in between different design runs. All right, but this is, the main point here is this is just an example of a commercial microaccelerometer system.
With mass production, how much does that typically cost? Is that something you can purchase? I mean, even in a lab to look at?
The accelerometers? Oh yeah, the accelerometers. I mean, if you were to, there's so many accelerometers. There's a bunch of them in your cell phone. The accelerometers you can buy now for probably $1 to $5. And the reason why is because they're so small, they take up very little real estate on a wafer. The thing that you do microfabrication on is you start off with a silicon wafer. They're about yay big. And then you make all your devices. Each wafer will ultimately end up containing, it could contain thousands of devices. The fact that the devices are small is what makes them cheap, ultimately.
And that's something you can easily integrate into something you're doing in the lab and use this as a platform to test.
Definitely. Yeah, the question is, can you buy some of these chips and integrate them into whatever system that you're working on in your lab? Yeah, yeah, of course, of course. Uh, there's so many test and measurement systems that are integrating accelerometers in there just because they're cheap, you know. And there's entire industries that have popped up because of this sensor. Like for example, the whole like Fitbit industry monitoring your it's like essentially a pedometer. That whole industry has come up because of this accelerometer device.
Because they're so cheap.
They're so cheap, yeah. They're dirt cheap and they're super small.
So that diagram you show up on the right, those are all ones basically looking to improve the accuracy because they all kind of measure the same. There's like one, it kind of shows like what, 1, 2, 3, 4, 8 different.
Which you're talking about this here?
You said that.
Oh yes. There's two aspects of that I should clarify. One is the differential sensing aspect of it, right? So when this is moving up, this capacitance is decreasing, this one's increasing. I'm sorry, this one's increasing, this one's decreasing. That's the differential part of it. The reason they have multiple legs on here is to increase the effective capacitance. So these types of sensors will become more sensitive the more capacitance you have. So by putting another leg here, they have a second capacitor here. They're getting a larger capacitance change when this plate moves. That's making making the system more sensitive. So this is an example of an accelerometer that's only moving in a single axis, and this one here below, you can imagine how this type of idea can be extended to double and triple axis sensors. So this is the example. Now, what we're interested in is how can we model these devices and what are the scaling benefits of these devices. All right, so this is the equivalent circuit modeling of an accelerometer. And I think for clarity's sake, I need to make a change here. So just give me a second here. Okay, so let's assume that this entire accelerometer package was subjected to acceleration. So you took the thing and you pushed it down. All right, so this mass experiences an acceleration force going down. The spring and the damping force resists that force. So there's force balance. We saw that in the previous slide. This is the mechanical model over here. So we have the mass, and then we have the spring constant, and then we have the dashpot here. All right. Proof mass experiences a force when the device experiences acceleration. Force is equal to ma. There's two opposing forces. The cantilever serves as a spring, so the spring force is equal to kx, and the spring constant we can calculate. And the velocity of the proof mass in the air creates drag forces, and this is called damping. Fd is equal to b times v, the damping coefficient. So the question is, how can we model this using a circuit? This is an equivalent circuit model. Just so we can give a little bit of context here. Remember in this slide here, we were showing the flow analogies of charge, fluid, and heat, and we were showing that you can model these different systems with electrical circuits, whether you're talking about electricity, the flow of fluid from one place to another, the flow of heat from one place to another. In my opinion, the fluid flow and the heat transfer are pretty straightforward. They're straightforward analogies because you imagine current, the same thing as fluid flow and the same thing as heat flow. Okay, so the different energy domains, when we were looking at our flow variables in electrical systems, it's current. In fluid flow, it's volumetric flow rate. In thermal systems, it's heat flow. These are all flow type things. It's very intuitive to understand. Okay, and when we talked about the different resistor elements, here you're talking about the electrical resistance, here you're talking about hydrodynamic resistance, and here you're talking about thermal resistance. Again, in my opinion, quite intuitive to understand. In the mechanics domain, when we make equivalent circuit models, there are two different analogies that we can use. We can use and the one that I'm going to talk about in this class, which in my opinion is more intuitive, is the force current model. It's less, I have to say, it's less intuitive than the electronics, the fluid flow, and the thermal models, because when you're dealing with mechanics, you're not really thinking about something flowing from one place to another. If we think about this rigid body mechanics problem, we're thinking about just the movement of the mass, period. There's no flow of one thing to another. Okay? But it turns out you can model mechanics using circuits, and it's done all the time. What you do is that you consider that the potential variable, so the voltage at a specific node in the circuit, you consider that the velocity. The flow variable, you consider that force. Okay. Now this is all mathematically, you can justify it. I'll show you in just a second. The resistor becomes lubricity, right? 1 over B. So this represents a friction element. Now, resistors always, in circuits, resistors are the energy dissipative element. And there's some type of energy loss going on if you have a resistor in the circuit. In the mechanical domain, the way you lose energy is by friction. So whenever you have friction in the system, that could be modeled by a resistor element. Now, in the electrical system, we have a capacitance. That's an energy storage element. Remember, in the thermal domain, we were talking about heat capacity, the fact that an object retains, that it takes energy to heat up an object. So that represents energy storage. Now, in mechanics, the energy storage element is mass. Because when a mass is moving at a specific velocity, it has inertia. It has kinetic energy. All right, it has momentum. Right? That momentum itself is a form of energy storage. That's why this can be represented as a capacitor. Inductor is also an energy storage element. We didn't really talk too much about inductors in the fluid flow and the thermal domain, but we all know what inductance is in the electronics domain. It's energy storage in the form of a magnetic field. In the mechanical domain, the spring is represented by an inductor in the force current modeling mechanism. Whatever the spring constant is, the compliance is 1 over K. And K is the spring constant. And this is represented by an energy storage element. The idea behind the spring is that if you were to take a spring and you wind up the spring and you push the spring down, it's storing energy. When you let it go, the mass springs away. So that's also a form of energy storage. All right? So we can model the mechanics system in terms of these two energy storage elements. So let's go back up to here, and we'll see how this system can be modeled. Where'd my pen go? Oh, there we go. All right. So if we look at this electrical circuit here, I actually had a. Let me write this down. I think this is a good way to understand it. So the mechanical system here, we have. I'm going to redraw this here just so you can see it. Mass, spring. All right. So this is the dashpot. This is the spring, and this is the mass. So this mass is subjected to an acceleration. Okay, so we're going to assume this mass is being accelerated upwards, and the spring is going to resist that force. The dashpot is also going to resist that force. So if we were to write an equation describing this, we say that the force the acceleration force minus the spring force minus the drag force is equal to 0. So the acceleration force is equal to ma. The spring force is kx, and the drag force is b times v. So this is equal to 0. So this becomes m dv dt. minus k. Remember, acceleration is dv dt, right? Displacement is the integral of the velocity minus v times v is equal to 0. All right, so we have this equation here in terms of one variable, the velocity v. dv m dv dt minus k integral of v minus bv is equal to 0. So that's an equation describing the system. Now, in the electrical equivalent model, just draw this out here next to it. The way that we describe this system is through this electrical equivalent circuit that looks like this. All right, on the left here you have a spring. That represents the energy dissipative element. Now the resistance is equal to 1 over B. Well, let's just say this is a resistance R. This is L. This is L, sorry. And this is C. What I want to show you here is why the electrical circuit can model this mechanical domain. Now, in this circuit, the way that we would analyze it is that we would use Kirchhoff's current law. Okay, Kirchhoff's current law states that all the currents in the system have to add up to 0. So let's say we do Kirchhoff's current law at this node. Right? KCL. Let's see. So this is I2, I3, and I1. So I2 equals I1 plus I3. Or, sorry, let's see. I2 minus I1 minus I3 equals 0. So this is Kirchhoff's current law at this node. I want to show you how this matches up. Okay, if we're for those of you who are electrical engineers, you'll see this find this analysis relatively straightforward. This I2 for a capacitor, I is equal to C dV dt. All right, and this is V is the voltage at this node. Let me redraw that. It's looking messy. All right, so this I2 here is going to be C dV dt. I1, the resistance, the current through that resistor is going to be, for a resistor, I is equal to V over R. So it's going to be, let's put 1 over R times V. And I3 here, if you recall the current in an inductor, there's this rule V equals L di dt in a circuit. And so the current, if you solve for it, it's equal to the integral of V divided by L. So this was 1 over L times the integral of V. This is equal to 0. All right. Let me just switch these two around just so you can see the, let's make this I3 and make this I1. 1 over R times V. This is just so you can see the analogies between the two equations here. All right, so if you look at the left here, right, m dv dt minus k integral of v minus vv is equal to 0. You notice that this equation is pretty much the same. C dv dt minus 1 over L times the integral of v minus 1 over R times v is equal to 0. These two equations basically have the same form. This is the reason we use equivalent circuit modeling. Okay, if you solve one, if you can solve one system and the equations are the same as the other system, those results can be used in the other system, right? We use circuits because circuit models help develop intuition. After you've been working with circuit models for a while, you develop an intuition that if you change this resistance here, then it'll change this performance of the circuit, and so on. The whole point is to develop intuition. But just so you see the equivalence here, right? We can say that number one, we can say that this voltage represents velocity. So this capacitance here is equal to M. C is equal to M. That's this thing here. Now the inductance, the L, is going to be equal to 1 over K, so that it matches up with this K integral of V over here. And the resistance, in order to make this match up with negative B times V, the resistance will be equal to, resistance is equal to 1 over B, and B is the damping coefficient. Right, so this circuit really does model the same thing as a mechanical system. So this is the diagram of the circuit here. Now, why did we go to all that trouble? Well, first of all, just to show you that how you can model these types of systems with circuits, but also, from this standpoint, once we have a circuit, we can analyze that circuit to determine the behavior of the system. So, in a circuit element, you know that we have these things called resonances, right? In the mechanical system, we also have resonances. With any RLC circuit, the resonant frequency is equal to, this is the given in terms of radians per second, is the square root of 1 over LC. And if we plug in the values for L and C, we find that in the mechanical system, the resonant frequency is the square root of K divided by M. All right, so just looking at this, what do you think is going to happen in a mechanical system as we miniaturize it? What will happen to the resonant frequency? If we have a vibrating object, we make that vibrating object smaller, what's going to happen to the resonant frequency? It's going to go up. It's going to go up quite significantly. Look, we have the mass on the bottom, right? Mass is proportional to length cubed. We have the square root of that, but still it's in the denominator. So this is going to be, resonant frequencies go way up at the microscale. This is one of the scaling advantages. Another thing here, we have the quality factor. Now, quality factor represents this idea of how much energy loss is in the system. If we were to tap that, mechanical system and it starts vibrating, if there's energy losses, if there's damping, those vibrations are eventually going to disappear, right? But in a perfect system where there's no energy loss, that thing will vibrate forever. Now, something that has very low damping, very low energy loss, that's called a high quality system. This is governed by, or it's quantified by this quality factor Q. The higher the Q is, the less damping, the less energy losses there are in the system. When we make resonators for sensors, we want them to have a very high quality factor. We don't want energy losses in the system. Right? So when we talk about the quality factor scales as square root of M times K divided by B. So you see this square root of M here at the top. However, you also have the B at the bottom. When you make the devices small, the damping coefficients get smaller because there's less air resisting the movement of the mass. So you can still get very high quality factors at the microscale. So just to sum up this slide before we go on to more of these resonant systems. In the equivalent circuit model, we can sum up the forces acting on the proof mass similar to Kirchhoff's current law. The voltage at the node represents the velocity of the mass. So in Kirchhoff's current law, we sum up these currents just as in the mechanical system, we always add up the forces. In the mechanical system, the sum of all forces acting on an object is equal to 0. In the electrical circuit, the sum of all the currents entering a node of the electrical circuit must sum to 0. So that's what we're using as the analogy here. Okay. If you're confused about this, if you model a few problems using equivalent circuit models, you'll see that it is in fact it's quite useful. So let's talk more about the scaling advantage. Higher resonant frequencies means a higher quality factor. Resonant frequencies scale as 1 over LE times C, or the square root of K divided by M. So this scales as L to the negative 1. Actually, that's not quite correct. It really depends on how you're scaling your spring constant and your mass. If you're just looking at the mass scales as length to the negative 3. Then you have the square root of that, which is 1/2. So scales, if you're just looking at the mass, and it scales as negative 3/2, length to the negative 3/2, which is still quite significant. You also have to look at how the spring constant scales as well. But why are high resonant frequencies good? Well, if you have devices that are operating at high resonant frequencies, it turns out that they're very useful for making resonant sensors. Now, let me give you an example here. Mathematically, we look at this, we say the resonant frequency is a square root of K divided by M. Now, if the mass were to change, the resonant frequency is also going to change, right? If you're working with if your mass is very small to begin with and your resonant frequency is very high to begin with, it turns out you can detect very, very tiny changes in mass, like incredibly small. The best mass sensors on the planet right now are these types of resonant mass sensing devices. What you have is you have a microfabricated device that has, it could be as simple as a cantilever beam. You can see that this is a simple beam element that's overhanging the side of a substrate, and that is being actuated at its resonant frequency. You can have a circuit that drives the system at its resonant frequency. This particular device is using a magnetic force, so it's running a current through here, and when that current is exposed to a magnet, it causes a Lorentz force, which pulls the beam up and down. This is a more conventional approach where they use electrostatic actuators. We saw examples of electrostatic actuators with the micromirror arrays. You have two capacitor plates, you apply a voltage between them, that causes the plates to go towards each other. It's the same idea here, except you have a series of beam elements here. You apply a voltage between this element here and this element here. That causes the attractive force between the plates, and that causes the device to resonate in the in plane. So it's sort of in the y direction here. I'm sorry, in the x direction. This is what an example of the device looks like. Because it has a small mass, it has a high resonant frequency. These devices are even smaller. These are just single cantilevers, all right, that are also resonating. Now, the main point I wanted to get at here is when the masses are small, the resonant frequencies are very high. We actually have the ability to detect very small changes in frequency. One of the things that we can measure very well using the instrumentation that we have today is that we can measure very small changes in frequency, because we have circuits that can that are very good timing circuits that can detect small changes in frequency. These elements, what happens is that even a femtogram change in mass can cause a significant change in the resonant frequency, and we can detect that. So these types of resonant biosensors rely on that idea. You have this cantilever that has a certain resonant frequency. Then you expose that cantilever to some type of biological or chemical agent. All right. Let's say the cantilever is exposed to a certain gas, and those gas molecules adsorb to the surface of the cantilever beam. That will change the cantilever beam's mass, right? Resonant frequency changes. We can detect that. Turns out that we can detect as little as tens of femtograms. Femtograms is 10 to the negative 15 grams. You can imagine how small that is. You can detect very, very small mass changes with these devices. It's quite amazing. You can also detect biomolecules. Now, proteins, DNA, these types of biomolecules can also attach to the surface of these cantilevers. In fact, you can get fancier, and you can functionalize the surface of these cantilevers. Functionalizing means if we want to detect protein A, and we don't want to detect protein B, we only want to detect protein A in a solution that might contain protein B and like thousands of other proteins. What we can do is we can put an antibody on, we can coat the cantilever with an antibody. That antibody will only attach protein A, the one that we're interested in. These types of surface functionalizations are very, very specific because in your body you have antibodies and antigens. The interaction between an antibody and an antigen is very, very specific in your body. So only certain cell types will connect to other certain cell types. I don't want to get into all the biology of that right now, but just suffice to know that you can make these things very specific. So what you would do is you could take this type of biosensor that's coated with an antibody specific to the protein that you're looking for, and you just dip it in a solution, dip it into your sample, right? Those proteins attach to it, and that changes the mass of the cantilever. Now you take your cantilever out of the solution, you remeasure its resonant frequency, and now you have a different resonant frequency. You can measure the amount of protein on that cantilever down to femtograms. Okay, very, very sensitive mechanism. It relies on the favorable scaling of resonant frequencies in microscale devices. I also want to mention this thing about quality factor. I'm just going to go over this very briefly. We may get into more detail on it later. Some of this may look familiar to some of you. So this is time on the x-axis. Now, let's say we have a system that is over-damped, and then we resonate it in time. What will happen is that the oscillations will eventually they'll die down like this. So this is over-damped. In an underdamped system, where we have fewer energy losses, these oscillations go on forever. Now, in the frequency domain, this looks something like this. So if we were to look at the frequency and what's called the power density, in this overdamped system, we see something that looks like this. Where this is F naught. This is the resonant frequency of the system. So these types of plots, the power density plots of spectral density, you have frequency on the x-axis and the amount of power contained at a certain frequency. If you have a device that's resonating like this at a specific frequency, then what will happen is that you will have your spectral power density plot will look something like this. The highest amount of energy is contained at F0, the resonant frequency. When the device is oscillating at that frequency, then you have a peak at F0. In the case of, so let's say this is what's called a low low Q system, and this is high Q. In a high Q system, you'll have a peak that's much sharper, centered at F0. This is also the power density. If we have a sharper peak, it allows us to measure the resonant frequency much more accurately. In a high Q system, we can measure the resonant frequencies much more accurately. Unfortunately, I think to give this a proper treatment, we could spend an entire lecture talking about quality factors and resonant frequencies and so on. I think for now, we'll just leave it at this. A low Q system will have a relatively wide spectral band, so which means that even though the system is resonating at a certain frequency, there is some power in the system that's also present at other frequencies. In a high Q system, all the energy of the mechanical system is right at the resonant frequency. Okay, this makes it easier to measure the resonant frequency. There's less energy losses in the system, and it turns out the system is much more accurate. So the quality factor has to do with the width of the peak divided and the height of the peak. The larger the height of the peak, the smaller the width of the peak, the higher the quality factor. All right, so just to sum up this module then. So the main points here. So I hope that you've seen some of the benefits of miniaturization. It's not just being able to make things smaller and cheaper and to be able to make a lot of devices on a wafer, but there's a lot of physics that improves at the micro scale. Okay, we've spent a lot of time on this module, but I think in terms of the rigor of understanding micro devices, I think this is very important for you to understand, regardless of what area of microengineering you end up going into, whether it's something that's very chemically focused or whether it's in the thermal domain, mechanical domain, whatever. The physics changes at the microscale because of the relative importance of the length-dependent phenomena, the surface area-dependent phenomena, and volume-dependent phenomena. And the way that we can understand that is by analyzing the governing equations, how the respective phenomena scale with length. So that's an example that we did earlier. We just wrote out the equations and found out the different factors that were geometrically dependent. And we can see how phenomena scales with length. That was your assignment. In some cases, we also saw that you can gain some intuition by looking at dimensionless numbers. Things like the Bond number, the Reynolds number, the Peclet number. These are typically used in analyzing fluids and heat transfer, but there's no reason that you couldn't have similar dimensionless numbers to analyze other domains. All right, these dimensionless numbers allows us, it's a very intuitive way to understand how one phenomena is more significant than the other phenomena. And then finally, another way that you can analyze it is just by doing these equivalent circuit models. And these circuit models aren't limited to microscale analysis. Any type of analysis you can do with circuit models are also called lumped element models. So you can use those to analyze microsystems in multiple domains. So what I hope you'll get out of this is that you'll understand that the different domains, as different as they are physics-wise, there's actually a lot of similarities between them. The way that heat flows is very similar to how fluid flows, very similar to how electricity flows. If you can understand some of those analogies, then when you start analyzing problems as interdisciplinary engineers, people in biomems, most of the folks have learned about different domains. There's a certain level of interdisciplinary expertise you have to have. You may not be an expert in all domains, but if you understand your own domain very well, you can extend that knowledge to other domains. That's the whole point of this exercise. Okay. All right, so let's end there.